So good day, Nathaniel Osgood. This is lecture 1 on aspect-oriented programming, which I'm delivering as part of my class CMPT 470, 816. And I want to begin by thanking former master student Jiva Paudel for his contributions to this set of slides, which many of which I've retained from an earlier presentation he gave a number of years back. So the broad setting associated with this work and motivation has to do with these concepts of abstraction and modularity that we've been pursuing in CMPT 478-16 in many different forms. We've articulated the ways in which abstractions in achieving modularity can offer benefits to programs in the ways that separation of concerns by providing unified places to handle certain types of issues in a program and having other issues handled elsewhere can be beneficial. And we've seen how we can use functions, including higher order functions, to capture certain types of functionality. And similarly, classes can capture certain sort of sub-areas, of vertical areas of functionality that are required within a program. However, there are frequently cases within programs where these structures, classes and functions, even with higher order elements, cannot effectively modularize or isolate certain types of needs, certain types of issues, certain types of aspects, and where code is kind of the code of concern is instead scattered throughout a program, despite our best attempts at modularity with classes and functions. An example would be logging functionality, or tracing functionality, or security functionality, or transactioning functionality. These sort of mechanisms, rather than being confined to just one place in our code, in a traditional object-oriented or functional decomposition context, those concerns are scattered throughout a code base, because after all, many different functions, many different classes need to log, or need to engage in transaction management, or need to reason about security related issues. So there's many cases where certain types of considerations, certain types of aspects cross-cut across our program. There's the same sort of need, as it were, in variant forms that appears across many classes, appears across many functions. Now, there's many ways we could try to capture this functionality, and as time allows in this class, we might talk about mixins, particularly in the form of Scala traits, as realized by Scala traits, as one way of capturing this functionality. A way to mix in functionality into a program without bringing with it the obligations of subtyping in the form of adhering to the Liskov substitution principle. Mixins allow us to kind of mix in areas of implementation into our code base, and allows in a way that allows for reuse, but is not burdened by the need for Liskov substitution principle to be observed. But another way that we're going to be exploring in this lecture is through aspect-oriented programming. In contrast to Mixins, aspect-oriented programming has a number of benefits. Even in Mixins, you need to be explicit about where we want to use this mixin. When you need it in the code, you need to state where that is. Okay. By contrast, in aspect-oriented programming, we can actually dictate when we characterize the aspect, this cross-cutting functionality, where we want to mix it in the code. that receptor code doesn't have to indicate explicitly, I need that. So we can mix it in wherever, for example, a certain pattern is matched. And this affords us a certain economy of specification and can help lower the risk of certain types of programming errors. We're going to see how aspect-oriented programming does also provide in the form of aspects, certain types of abstraction that will support some useful functionality. So, for example, we might have in a given program, this an example I believe from Jiva's thesis, certain types of functionality scattered across a code base, and rather than leaving it scattered across the code base here and hither and thither, trying to go find it and update it in many modules, think about security or logging or transactioning. Instead, ladies and gentlemen, we can capture it all in one place in our program. We can modularize it. Not only that, we can state in this area of our program where elsewhere in the program it's to be woven in a very general way. So if a new module is added, it can automatically have the requisite functionality woven into the new module, rather than depending on the programmer to remember that it has to be put in there. Or here we have many types of cross-cutting functionality, each shown in a different color, and we might consolidate that to different concerns, all consolidated in a modular way elsewhere. Okay, so we've reduced this cross-cutting functionality, although we haven't yet eliminated it. Okay. And so we're going to be talking about a couple components of aspect-oriented programming, some of the basic concepts, introducing the concept of join points, which are going to, which are special points of significance in the flow of the program, where we may wish to have interesting things happen. Things like just before a function call, or just inside that function call, just before it returns, etc. We're going to see intertype declarations, although probably those will be in the next lecture, where we statically weave in some functionality, we extend a class with extra features. And we're going to see how we can use interception in the form of aspects at join points to put in place some new functionality. Okay, and how we can do it in a modular way with aspects. Okay, let's take a look at join points. These are points of significance in the execution of a program, in particular places within a program as it dynamically executes, where there's often particular interest. Okay, so perhaps, for example, we call in to move for a line, and it executes a method, and that calls on to move for a point here. Okay, so we have one method execution here, and it in turn delegates, moving the line, delegates to moving a point. This is a bit of code here. We have method execution coming in and method call going out. Okay, and there's some notable join points here, and they're shown in these little purple things here. So when a method is executed, marking entry to the method coming into it, or when a call is made, or when a second method execution occurs here. These are points that might be of interest in the sense that important things have to happen there. Certain functionality needs to be accomplished. Maybe it's opening a new transaction, starting a new transaction, or maybe it's checking some security. Similarly, coming back the other way when we have return, we have points of return or throwing a value, throwing an exception from here, returning here and returning there. So at these places, calls, method executions, returning or throwing, there may be things we want to do. Maybe we we want to take whatever value is going to be returned and we want to substitute it with another value. Or maybe we want to handle a certain exception that occurs. Or maybe we want to log when we come into a method, we want to log it out to a file. Or when we're going to make a call. So these would be things that might be of considerable interest. So these are method execution join points we're looking at here. Okay, and we've seen some of them: method and constructor calls, method and constructor execution, gets and sets to fields are another thing. We're going to set or get the value of a field. We may wish to catch those and perhaps log them. Perhaps record the values that are set and get, that are obtained there or set. Maybe we want to record every time a certain field is set for the sake of debugging, right? And we want to know whenever it's set so we can trace down this puzzling fault that's causing some failure in the program. Execution exception handlers when we execute, when we initialize code, and some other constructs we may come back to later. Okay, so let's take a look at a program. Here's a program. Here we have static void main, and this calls up an instance of class example and executes a function on it. Now, in the process, it's creating a new instance of example where this constructor is initialized, ladies and gentlemen. So within this context, we have a number of these join points. So one before the execution of this, and before the call to this constructor, right? And 3 here within this call to this constructor before its execution, after the set, so before the set and after the set. So before actually the set is performed to this instance variable, and after it's performed, and then returning here, and then just after this call to this constructor, just before the call to this method on this instance, and then just inside of this, before the execution, and here before the get, here we're getting a value, a field value x here, and then after the get, okay, and then after that execution of this method, and then here again after the call here, right, after this call to func and after the execution of this, okay. Here, ladies and gentlemen, we're going to be defining here different spans associated with some of these constructs, for example, within code and within. And we're likely to come back to that later, though probably not in this presentation. Okay. And so we're within certain code, for example. Okay. So, ladies and gentlemen, we're going to then specify. So these are join points. These are conceptual structures that exist out there, and we have a way of naming them or referring to them that are called point cuts. Join points exist whether we name them or not. They're points of significance within the execution of our program. But we actually name such join points or specify them by using this construct called a point cut. Okay, so if we want to, for example, refer to any calls to these functions, set P1 and set P2, we can define a point cut. In this case, it's called move, where we refer to calls to this function here, calls to this function. These are the functions up here. We just say, okay, move refers to these specified join points where we are calling off to this function, much in the same way where we are calling off here, for example, to a certain method. And as we'll see, we can specify before and after these point cuts, much as we said before this call, and after this call, 8 and 13 respectively. Okay, ladies and gentlemen, so by specifying a point cut, we can then refer to a certain place in the code and have qualifiers like after or before that place, or around in some cases. Okay, here we have what's called the composite point cut. It is two conditions. So this refers to cases where either we're calling set P1 or we're calling set P2. Now, it can be useful to kind of think of point cuts as specified in kind of a constraint language. We're specifying constraints that need to be matched. In this case, they're particularly simple constraints for it to qualify as a legitimate instance of the move point cut. Okay, and there's kind of this constraint language that match join points to satisfy certain constraints. And in some cases, the constraints can be more sophisticated, for example, involving some pattern matching of sorts. When we match up a certain point cut constraint, often what we're going to do is to bind variables. So we're going to sort of match it up, and in the process we will unify or we'll match the values of certain variables that have remained unbound so that they take on values for that particular instance of this point cut, that particular join point that matches this point cut. Those variables will have values specific to that context. And if we have another join point, point cut will match there, and there may be different values to those variables for that context. Okay. Okay. So imagine we have this instance where we have a class of points and a class of lines, and then a triangle class. And you'll notice that there's some composition here, so or some reuse here of these lower level constructs, namely point, by the two higher level. By triangle, it uses points, and line uses points. And while a bit contrived, the example here posits that we have classes, we have points that can be moved. These are not immutable. And then we can request, for example, setting the points associated with a line, okay? And we can also do move by for a whole triangle, translate it by dx and dy, okay? Some distance x and y. I believe this should be here that if these things are not both 0, it says if this is not equal to 0 and that one, but really what we want to check if they're not both 0. Okay, that's going to appear in several slides here. Okay, now you can imagine if we're dealing with this in a graphical context, we might need to, when we're setting the location of a triangle, we're moving it, or we're setting the points associated with it, or setting the points associated with a line, or we are updating the values of points, we may want to give some visual feedback, feedback that displays the new update for the points, for example, okay, the new location of the points. So at these cases where we're performing these updates, we're going to have this call to display update, which is basically going to refresh the current display so that it stays current. It reflects the latest locations of the points, the lines, and the triangles, ladies and gentlemen. But you'll notice that these display updates these are occurring at many different places. They're scattered, ladies and gentlemen, in the code at many different places. And conceptually, and this is just the rub, or this is just the point, they're conceptually very similar in their needs. Basically, when we change something in the underlying model, we need to update the display to stay current with that and to remain current and to reflect that updated model. But even though it's a consistent, simple idea, to wit, when we update the model, we have to update the display, it's scattered, ladies and gentlemen, throughout the code in a most unseemly fashion. It's not modular. This update is occurring all throughout this code base at many different points, but at certain conceptually sort of consistent points, at certain points that are all conceptually delineated by the idea we're updating the model. So the idea here is going to be that we're going to define a point cut, which is going to indicate the set of locations, set of join points as specified by the point cut, where these display updates must occur. And by specifying this, ladies and gentlemen, in a point cut, we're going to be able to introduce some logic there that will handle it in a consistent way. And that logic, rather than being scattered throughout this code base, is going to be in one place. It will say display update when any of these things are changed. And in some cases, we might try to formulate more general rules whenever we set something, whether it's P1 or P2 is immaterial. Whenever we set something, set a property, maybe we want to do a display update. We could specify a more simple rule. Okay, so we're going to have this point cut with move here. Now, ladies and gentlemen, I had noted before that just as we had here the ability to sort of distinguish, okay, this is 8 is just before a call, and this is 13 just after a call to example func. We want to be able to often delineate things just before and just after point cuts. So if we have a point cut called move here, which doesn't have any information that it's kind of associated with here, that it's collecting data on, we can have things that are just after the move, just before the move, or in fact around the move, okay? And so here, what we can do, for example, is if move delineates something which returns a value, in this case it doesn't, it's void, but if it returned a value, we can actually replace that value, okay? But the point is we can do things before or after or around the value. We can replace a value, we can print out a message, we can log it to a database. Lots of different things we could do before and after this this move. Okay, we might audit some information, etc. And so, you know, we'll within advice, which are pieces of code that will specify what to do in different join points. We'll have a point cut, but then also qualifiers like whether it's after it or before it or around it. Okay, and we may have a named point cut, or we may have an anonymous point cut. Okay, so for example, here's our point cut. We might say after returning move, and this will, after returning, this after move is returning, we will then execute, ladies and gentlemen, the code. Okay, so it's sort of running it on the way out. Okay, so just after it's returning, we are going to return things. So here, this is, you know, after a call, we could perform a value, and that will allow us to to handle just after this call will be we can execute some code here. Okay, we'll maybe log it. Okay. Now, this so-called advice, together with the point cut that it's using, is defined in the context of an aspect, and this is actually a class, and it specifies a cross-cutting concern. And so this advice is paired with a point cut declaration. In this case, and it can be 1 or 0 or more. We might just manually specify the point cut rather than naming it here, and this is bundled together in an aspect, which defines the point cuts in which to intervene and what to do around them. Okay. Okay. Now, it turns out that the plot thickens here, ladies and gentlemen, because there are times where we will wish to elicit information at certain contexts. Remember, point cuts specify join points, which are dynamic quantities while the program is executing. And for a given join point, ladies and gentlemen, we might want to collect certain types of information. Maybe we want to log who the caller is for this call, or some information on who the target is, the object in which this is being called. So, there was some code executing inside of this previously, and then it called a method, say on an object O. We might want to capture that information in the context of a call. Notice this is a kind of wildcard pattern that can match many different types of things. Now, an example would be so we can capture that information, or we can capture arguments. So, for example, if we have set x, y here, and this occurs when we're calling set x, y in some figure element, having two values, it's going to bind the values of x and y here. So whenever we call this, it'll be with two particular values, and by capturing these, by binding to them, and binding to the target, whatever this was called in, the figure element, this guy here, we can then use that information within this figure element. For example, we could trace, say, okay, this figure element was moved to this certain location. X, Y, and FE were kind of bound to, were matched here, and given, found their values here for a particular call. And of course, the values of FE, X, and Y will be different for particular instances of this point cut. Different join points in the dynamic execution will have different values of X, Y, and FE over the course of a program's execution. But we can log them. For each one of them, we've abstracted these out. So for each one of them, we'll get the values here. They're parameterized, so we can get them, and we can log them out. Okay? So this is an advice declaration that is specifying for this point cut, we wish to use this point cut, and you'll notice that it is parameterized by the advice by FE, X, and Y, which are then going to be matched in the context of this point cut according to these rules. Okay. Okay. So it's kind of a pattern matching syntax, as it were. Again, these aspects, these point cuts specify sort of constraints and pattern matching constraints, almost in terms of how values are bound in a particular context. It has to match this criteria, and if so, we'll have FE, X, and Y bound, and those will be used here and printed out. Okay. Okay. So, ladies and gentlemen, here we might have a move, which is associated with a mover in a certain shape that is moved. Okay. And here, the mover is the thing that called this function on some object to be moved, some shape. And that's used, and then we'll call display update using this information. Or if we don't need to do that, as was the case back here, if all we want to do, is call display update, then whenever one of these move point cuts is realized, we'll just call display update. Boom. This is a more sophisticated one. And not only that, we can actually capture the return value, ladies and gentlemen, of a given method if we want. Here's a join point returning some object, and we can log what that return value was. Think about that for debugging, or that for testing, for example. Okay. Ladies and gentlemen, another type of a point cut is a round. And in a round point cut, we have a call. We call to it, and then we can intercept that. And for example, we can end up, if it has an argument new x, we can make sure new x is greater than or equal to some minimum value, less than or equal to some max value, and we can then proceed on with the value checked to make sure it's in this range, or constrained to be in that range. Have to double check if this is actually essentially forcing it to be in the range, or just checking if it's in the range. Okay, so ladies and gentlemen, just to think about a hello world program, we could have hello here and world. Hello is a class. The aspect is world. And this specifies a point cut following hello. So following call to main here, just after, at this execution. So this is specifying the execution of main. And just after the execution, ladies and gentlemen, we're going to, this is the advice, this is the point cut, just after this point cut, we're going to print out world. So this is going to print out hello, and just after this leaves, it'll print out world. Just after it executes main, it will print out world. Aspect will print out the world part, hello will print out the hello part. Okay. Now, what's going on here beneath the covers for AspectJ, the Java-based implementation of aspects, is we have some code put into place, ladies and gentlemen, where we're going to have the original code, but where we're going to then call, ladies and gentlemen, this aspect here. So when we run an AspectJ compiler, it weaves this code into this code, and it does it in a very consistent way. So if the execution proceeds normally and there's no exception thrown, we will then call off to this advice to print out world. If, on the other hand, an exception is thrown somehow in here, or something whacked out about the stream or what have you, we can then call off. It will also call off to print this out and then proceed to continue to throw. So it's intercepting, ladies and gentlemen, what's going on here in a clever way, so that it calls off properly to this print associated with world. Okay, and in this code that it's calling off here, it's going to print out world. Okay, so this is how this aspect got woven into hello to modify this class so that it properly calls off, ladies and gentlemen, to this advice. Okay, so point cuts are useful ways of specifying join points. We could specify for many types of things, for exception handlers, for calls, for getting and setting fields, for initialization, and we could specify things before or after the point cuts. Okay, and by so doing, we could take code that was like this, where this logic, this common logic, had a common theme, a common motivation, intention to it, very consistent intention, but it was scattered throughout the code base. We could modularize it in one place and place it so to clean up this code. Instead of repeating this ad nauseum, maybe adding another method and forgetting to put this, we just have this display update in exactly one place, and we simply tell it where do we want to weave it in to this code. It will be woven in at all these different places. Okay, ladies and gentlemen. We'll continue on this lecture in a second lecture in just a few days. I hope that's been useful in helping you understand some of the basics of aspect-oriented programming. And we're going to continue on to look at a number of concrete examples of aspect-oriented programming and talk about some of its more subtle aspects, and talk a little bit about some of those things that I glossed over this time, like the C-flow construct. Okay, thanks very much, and I'll be back with you with another lecture shortly. Grateful for your attention.